So I'm coming back. So can you hear me and can you see my slides today? Okay, thank you so much. So now we finish session 1. Now we go to session 2. We discuss more on linear systems and invertible matrices. Okay. Of course, we know a system of linear equation has 0, 1, or many solutions. Okay, infinitely is many solutions. There are no other possibilities. Yes, of course. And then if we this is a square matrix. And this is invertible. You can get inverse of A. Inverse of A times B, you can get X. Okay. And we have some examples. Okay, just for your reference. Okay, so here we can determine A, X, and B. You can get inverse of A. Okay, we have two ways, right? We have AI, E, I, inverse of A. Okay, we apply Gaussian elimination. Or the second method, okay, we calculate inverse of A, EK is minus 1, blah, 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 times E1. Of course, we need to modify A to become A. Okay, after that, you can get X. A is the product of inverse of A and B. Okay. This one for your reference, okay? Yeah, just combine because just combine the coefficient matrix with many constant terms, okay? For example, here we have this is A, right? A is 1, 2, 3, 2, 5, 3, 1, 0, A. Okay, and this is the same A. We're the same A, but different constant terms. Okay, so we can combine. Okay, A with constant term B1 and constant terms B2. After that, we modify A become A, and then you can get B1 over commas, B2 over commas, like this. Okay. So this one is X. This one is the solution X. This one is the solution X. Okay. So this is the examples of this one. Okay. We have now generally AX is B1, AX is B2, AX is B3, blah blah blah. So we can combine many constant terms. Okay. Like this. Okay. We have matrix A, B1, B2, B3. Okay. And then if we modify A, B1, blah, 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 BK, become I. And here you can get the solution X1, X2, blah, 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 XK. I mean solution, not variable solution. This is the solution. And of course, here must be identity matrix. Okay. Yes. Okay. Because this is identity matrix, so this one is X3, right? This is X2, this is X1. X1 equal to 1, X2 equal to 0, X3 equal to 1. And then we consider this one, you get X1 is 2, X2 is 1, and X3 is minus 1. Okay. Yeah, any questions? Okay, continue. Then the properties of invertible matrices. Okay, yeah, A times B AI and B times A is I. So if A is a square matrix and B is a square matrix satisfy B times A is I, so B is the inverse of A. Okay, and A times B is I, so B also is the inverse of A. Okay, and we have many properties in relation to the invertible matrices. Okay, A is a n and n matrix, so A is invertible. If A is invertible, that means AX equal to 0 has only a trivial solution. That means all columns will be linearly independent. Okay, linearly independent. The reduced row echelon form of A is IN? Yes, of course. Okay, A is expressible as the product of elementary matrices. Yes. Yes. Okay. Yes. It's because A is square matrix. Okay, so A is expressible as a product of elementary matrices. Okay, so AX is B is consistent. Okay, that's mean we have the solutions. Okay, AX is B has exactly one solution for every n rows one column matrix B. Yes, of course. Okay, so yeah, up to now we understand the properties of invertible matrices. Okay, so determine the consistencies by elimination. Okay, but just observe some special cases. For example, this one. Right, for example, this one. For example, this one, we don't have the leading entries for the last row, so that means we have many solutions. So it's free for x3, right? X3 is free. So that means x3 is t and with t belonging to real number set. Okay. Yeah. Or we can say x3 is the function of x1 and x2. Okay, so finish session 2 and we have some exercise to practice exercise 5. Solve the systems by inverting the coefficient matrix. Okay, that means we know A, we get inverse of A, and then you can get X is inverse of A times B. Okay, solve the matrix equation for X. Very easy. Okay, here we have 3 and 3. Here we have 3 rows and 5 columns, so that means here you can get X in 3 and 5. Okay, 3 and 5. Here 3 and 3, here 3 and 4. Okay, so here must be 3 and 4. Okay, 3 and 4. Any questions? Okay, so session 3, we discuss diagonal, triangulars, and symmetric matrices. Okay, diagonal matrix. Of course, to determine the diagonal matrix, okay, the original matrix must be a square matrix. Okay, this square matrix. So diagonal matrix. Okay, the diagonal matrix. That means the diagonal element here, right? Yeah, the diagonal element here. The diagonal elements, of course, will be at the diagonal. So the other element, I mean the non-diagonal element. The non-diagonal element must be 0. Non-diagonal elements must be 0. Okay. This is special case. So they are diagonal matrices. Okay. So conclude. So A is a square matrix, right? A is a square matrix. This is the first one. And then on non-diagonal element will be zeros. Okay. So if these requirements are satisfied, we can get the diagonal matrices. Okay. And more generally, we can get diagonal matrix with n rows and n column. Okay, this is diagonal element, and non-diagonal elements will be zeros. Okay, we can guess the inverse of the. Okay, the inverse of these the inverse of every diagonal element. So if we know D1, we just take these 1 over D1, 1 over D2, blah, blah, 1 over Dn. Okay? So you can get the inverse of the diagonal element. Diagonal matrices, okay? And we take the inverse of diagonal element, you get the inverse of diagonal matrix. Any questions? Okay. So for anyways, if we know D, we can guess inverse of this. Very easy, right? We just take these reciprocals of diagonal element. Now to the power of k. Okay, so D to the power of k is E. This matrix. Okay, we take the power of k to on diagonal element. Okay. Of course, k's will be positive integers. Okay. So for example, here we have A. This is diagonal matrix, right? So we can get the inverse of A is E. These reciprocals of 1 over 1, 1 over minus 3, 1 over 2. Okay. The reciprocals of diagonal elements. The 0, 0, 0, 0, 0, 0. Okay. Here. A to the power of 5. A to the power of minus 5. A to the power of minus 5. That means A to the power of minus 1 and then 5. Okay. So inverse of A is E here. Okay. And then we take the power of 5, the power of 5, power of 5, power of 5, you can get 1. Minus 3 to the power of 5, you can get here, right? Right? Let me check. Okay, we have 1 over 3, and then to the minus, right? Minus. And you can calculate that to the power of 5. Yes, yes, correct. Okay, and then here you can guess the result very quickly. Okay, triangular matrix. Triangular matrix. Triangular matrix. So again, A is L times U. Okay, we have A is a square matrix for more meaning, you know. Yeah, so that means we have L, N, and N, and U, N, and N. Okay, like this, like this. This one is lower triangular matrix. Okay, and this one is upper triangular matrix. Or we judge for easy, you just say if lower, this is random, this is 0. For upper, this is diagonal, okay, and upper, so this is random, this is 0. That's all. Okay, 0. Or if A is not a square matrix, A is n and n different from m, you can get what? You can get L times U, and L is n times n, and U is n times n. Okay, that's all. So L is always this square matrix, always this square matrix. And yeah, I just tell you some steps to get the definition of A if I see a square matrix. Okay, or A m times n. Okay, we can get LU, M and M, and this E, M and N. Okay. Any questions? So far, any questions? Okay, next. Okay, we have some properties, but some descriptions. But you just follow the format. Okay, you can understand. Symmetric matrix. Okay, we have a square matrix A. Okay, it says to be a symmetric matrix if A equal to transpose of A. Okay, if A is transpose of A, we say A is a symmetric matrix. Okay, for example, here. Okay, this is A, right? So when we take the transpose of A, we can get, okay, the first row become the first column, so 1 minus 3. The second row become the second column, so minus 3 and 5. So A equal to transpose of A. Okay, so A is a symmetric matrix. A symmetric matrix. Okay, and this is special case, you know, because this one is diagonal. This is the diagonal matrix. So the diagonal matrix is definitely a symmetric matrix. Okay, this special case. Okay. Or we can say the symmetric matrix does mean this is diagonal element. This is diagonal with diagonal element. So 4 equal to 4, 5 equal to 5, 0 equal to 0. Okay, that means if we consider this symmetry, if we consider symmetries here, this one line, the line, right? The diagonal line, it is symmetry. Symmetries of this element and this element. It is symmetry of this element and element. So this one we say a symmetric matrix. Okay. Okay. Then the products of symmetric matrices. Okay. So we have two matrices A and B. So if A times B equal to B times A, we say they are commutation. Vietnamese meaning hoán vị. Okay, commutation. Okay. Yeah. So A is mutated to B or vice versa. Okay. So now look, we have theory. Let me see. Look, a product of two symmetric matrices is symmetric if and only if the matrix commute. The matrix commute. Okay. So now look. This is symmetric, right? This is diagonal. This is symmetric. This is diagonal. This is symmetric. Okay. So we have A, this is B. So A times B, you can get this one. But this one is not symmetric. Why? Why? Because A times B is different B times A. So the result is not symmetric matrix. Now, look. This one, symmetric, right? 2, 2. This one, 2, 3. So this one is symmetric. And then when we take A times B, we can get symmetric. Why? Because A times B equal to B times A. Now we check A times B here. And now if we take B times A, we get what? We get what? B times A. BA minus 4, 3. 3 is minus 1. AA 1, 2, 2, 3. Okay, this one times this one, we can get what? Minus 4, 6, get 2. This one times this one, minus A, 9, you get what? This one times this one, 1. This one times this one, 6, minus 3. Okay, the same. So B and A equal to A and B. And we say AE commuted to B or vice versa. Okay, so this example to demonstrate for this theorem, the products of two symmetric matrices is symmetric if and only if the matrices commute. The matrices commute. Any questions so far? Okay. Okay. So if A is an invertible symmetric matrix, invertible and symmetric. Okay, so inverse of A is symmetric. Okay, if A is invertible matrix, then A times transpose of A and transpose of A times A are invertible. Okay, yeah. Again, if A is symmetric and A is invertible, the inverse of A is symmetric. Okay, here we have A. Okay, so the transpose of A times A is here, and A times transpose of A is here. And this is diagonals, so this is symmetric. This is diagonal is symmetric. Okay. Okay, so session 4 for your reference, we just applied the theory of this lecture into the economy. But now we are engineer. We are in the electrical and electronic engineering, so we just give it session 4. Now for work, we have homework. Let me see. We have homework here. Find the inverse of an elementary matrix. You know, that means if we know E, we find the inverse of E. Okay. Find a sequence of elementary matrix. Okay. Whose product is given non-singular matrix. Okay. Yeah. So that means here I, right? We need to modify I become I, and then you can get the sequence. The sequence. So inverse of I is AK. AK minus 1, blah 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 times E1. E1. So here is the sequence. Here is the sequence of elementary matrices. Okay. Right? We have AI. Okay, to get I inverse of A. Okay. So now if I time E1 blah 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 E case minus 1 here and I become I. Okay. Yeah. So this one time this one you get this one time I, you get inverse of I. Okay, correct. Okay, and then we find this LU factorization of a matrix. Okay, yeah, of course, A must be a square matrix. Okay, for more meaning. Okay, and then use LU factorization to solve the linear system. Okay, so we need to factorize A become L times U, and then well A times X equal B, right? So that's equal to L times U times X equal B. That means you get Y U X. Okay, yeah, and L times Y B. You know L, right? You know B. You get Y when you when you get Y, you can get X. Okay, this is homework. Okay, and then so for Ax equal B by solving the triangular systems. Okay, I is L times U. Okay, yeah, here they don't use C or Y, they use C, but that's okay. C is Y, right? L times Y is B. And use this LU factorization of A. Okay, this is L, this one is U. Okay, to get X. Okay, to get X. Homework 3. Okay, they already give us L and U, right? L and U. But for the final exams, you need to calculate L and U for yourself. Okay. So we finish lecture 1, part 4, and we have now, maybe more than 10 minutes. Okay, so we just here we have some application of linear algebras. Let me see. Okay. Okay. So just introduce to you. So I remember we have another lecture to mention about this one. Okay. So we discuss about least squares regressions analysis. Okay, this one is very famous when we study machine learning. Okay, so if you study machine learning, we will come back to this regression analysis. Okay, so here just basic, here we have 1, 2, 3, 4, 5 boys. We have 5 boys. Okay, we have 5 boys A, B, C, D, E, and every boy we have 2 dimensions, the first dimension and the second dimension. Okay, so that means A we have XA and YA, B we have XB and YB, blah blah blah. We have E is XE and YE. Okay, so we would like to draw the curve. Okay, to draw the straight line. Okay, this is straight line. Okay, to fit, okay, on board here, very difficult, because actually these boys are not in the same line, are not in the same straight line. So we just find the good line. Okay, we need to find a good line to to fit on data points here. Okay, but actually very difficult. Okay, and you cannot. Okay, we just find the approximation, okay, of the straight line. Okay, yeah. So if here we have straight line, we can get the distance. Okay, the distance. Yeah, I consider the black curve. Okay, distance. Yeah. So for here, boy A, boy B, boy C, boy D, boy E. Yeah, so we have the distance between the point and the straight line. Okay, so if the total distance is small, is minimum. Okay, we can guess the least square regression analysis. Okay, minimum. So why we have squares? Because the distance maybe is the negative or maybe is positive. So when we calculate this square, so that means all the distance will be actually distance is not negative, but we take these squares. Normally for the errors, actual errors will be negative or positive. Okay, so when we consider this minimum distance, we take this square. Okay, yeah, like this. So you have some positive, some negative. So when we take this square, okay, you can make sure the errors is always positive. For example, we have 5 boys, right? And we assume we have this line, this linear curve. Okay, we have model 1, so we have fx is 0.5 plus x, and model 2 we have fx is 1.2x. We don't know method 1 is better or model 2 is better. We don't know. Now we check. This is boy A, boy B, boy C, boy D, boy E. For boy A, we have 1, 1. Okay, so if x is 1, okay, so we find error, right? Error, right? So if x is 1, fx is 0.5 plus x. So if x is 1, fx is what? 1.5. Okay, am right? So fx is 1.5, but y is 1, so we have the errors is minus 0.5. We take this square. Okay, now for B, x is 2. X is 2, you come here, you can get 2 plus 0.5, you get 2.5. But y is 2, so we have the errors minus 0.5. Similarly, For C, X is 3. 3 come here, you get 3.5, and Y is 4, so you get the errors is positive 0.5, and so on. And then we take this square. After we take this square, and then we take sum, you can get the total errors. The total errors will be 1.25. Now we consider model 2. X is 1, so Fx is what? 1.5. So we have the difference, right? We have the errors between yi and fxi, right? We take this way, as I mentioned before, we take this way because we would like to make sure the errors is always positive. Okay, so here you get this value, this value, this one, and then when we take the sum, you can get 1.0. Okay, so if we compare the total errors after we check this square, okay, and then we check sum of them, okay, you can get model 2 is better. Model 2 is better. Why? Because the total errors is less than the total error of model 1. Okay, so model 2 is better. So this one we say least square regression analysis. Why we say regression? We say regression because we have data point. Okay, we have data point. We come to data point. Okay, yeah, we regress the curve. Okay, so how can we regress the curve? How can we regress the curve, right? And how can we know this one is 0.5 plus x and this one is 1.5x? Later on I will tell you. But if we regress the curve, okay, we can take the errors, right? And then we take the square of the errors. This is square. Now I mentioned to use, I explained to use square. And then when you get the square of the error, we take the sum of all square errors, you get the minimum, and then least the minimum. Okay, so now we know what is the meaning of square because we take the square of errors. We know what is the meaning of least, right? We want to get the minimum of total error. Now, what is regression? How can you get the curve from the regression? Okay, so we think about we apply linear algebras. When we apply linear algebras, you can know how to regress the curve from the data point. Okay, now look. Okay, so now we think about linear algebras. So now we have many points. Okay, first point, second point, n point. We have n point. For the statistics, okay, n normally higher than or equal to 30 points. Okay, so the least square regression lies in the linear function because we study linear algebra. So we have the linear equation. We have the general linear equation like this. Okay, we have fx e a0 plus x1x. Okay, we assume we have the regression curve like this. Okay, so here we have many points. Okay, we have x1 and x2. Okay, we have two dimension, two dimension. Okay, we don't use x. We don't use we just use x and y, right? X and y. So we have point 1, we have x1, y1, point 2, x2, y2, point 3, x3, y3, and so on. We have many points. We need to find the linear curve. Okay, linear curve. A linear curve. We need to find the linear curve. Okay, to make sure the total errors square is minimum, right? The total of the sum of all square errors to be minimized. Okay, the minimum. Okay, so we minimize, right? We minimize the sum of a square error. Okay, so now if we consider point 1, you can get this error, right? Point 2, these errors, blah blah blah. Point n, this is the errors of point 1. Errors of e mean errors. error of ON. Okay. Okay. Or we can get this one. We can get this one. So y1. Okay. So if I analyze y1 become fx1 plus y minus fx1. That's okay. Yes. Yes. Because we plus fx1 and we minus fx1. The same. Okay. The same. So now I make this one together. I make this one together because actually y1 will be different from x1. Okay, so this one is error, right? So if y1 different fx1, that means y1 minus fx1 is e, like this, e. And then y2 is y2, I plus here fx2 plus here, and then I minus fx2. Okay, so I take the sum, okay, here, yeah, and this one is e2, and blah blah blah. You can get this one, I can get this one. Okay, and then I say, okay, ei is yi minus fxi. But this is more general, you know, more general. Okay. Okay. Yeah, this is the errors. So now y1 minus fx1 is 1, e2 blah blah en, and this is fx1. fx1 is what? fx1 is the general formula here, right? So fx1 becomes a0 plus a1 x1 x2 blah 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 blah, a0 plus a1 x2. So what is x? What is x? Linear equations, right? They are linear equation. Okay, they are linear equation. Continue. Now this is linear equations. Okay, x1 is variable. So if I analyze, so this one like constant terms, right? This one is x, and this one is a, right? Right. And this one is a. Okay, right? I modify. So here I can get y1 blah 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 yn equal to, you know, a0 and a1 are variables. We need to find it. Okay, so if here I say I have, okay, 1 x1 1 x2 blah 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 1 x and, you know, time 1 1 x1, okay, time what? Time a, look, time a is what? a0 and a1. Okay, and then plus what? e1 blah 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 to en, right? So that means if I just consider y1 is what? This one times this one, you get a0 plus a1 x1, right? Plus is 1. Okay, so I modify the linear equation to becomes the linear matrix. Matrices, right? The linear matrix, combination of linear matrix. Okay, linear combination. Okay, yeah. So here I say this one is I, this one is x, this one is a, this one is e. You can get this one here. Yeah, here. So now we have y a x times a plus e. Okay. So this is the regression model. Y is x times a plus e, you know. We need to find a. Why we find a? Because a contains the variables. We already know y. We know x. We know e. We need to find a. Okay, and then the coefficient of the least square regression line are given by the matrix operation, the matrix equation here. So now we can get a x transpose of x transpose of x times x, okay, to the power of -1 time transpose of, that means inverse of xt times x, xt and y. So if we apply this one, you can get a. If we know a, that means we know a0 and a1, and then you can get the regression curve, right? Regression curve is a plus a0, a0 plus a1x. Okay, a0 plus a1x. Here, this is the regression curve we defined before. Okay, so if we calculate a by these formulas, you can get the linear curve. But the question is, how can we know a is transpose of x times x to the power of -1? That means the inverse of xt x, xt y. How can you get this one? Okay, next lectures I will tell you why. We calculate matrix A, we calculate variables a0 and a1. That is here. Okay, a is transpose of x times x inverse times transpose of x times y. Why we have this one? Because if we know this one, we can get a, we get a, that means we get a0 and a1. If we know a0 and a1, you can get linear curve. Because we define linear curve is what? a0 plus a1x. Okay, but the question is, how can you calculate? How can we know this one? Okay, later on, I will tell you, or you can ask ChatGPT. Why? For the matrix form of linear regressions, A will be calculated by this. Okay, you can understand first, and then next lectures, I will explain to you why we get A here. Okay. It's very easy, but we don't have more times now. So of course we will stop. And this example, yeah. So after we apply this one, after we apply this one, yeah, you can get A. So this one is a0 is what? A0 is -0.2 and a1 is 1.2. And then you can get the linear curve or regression curve. So fx or y is a0 plus a1x. So a0 is 0.2 minus 0.2, right? Minus 0.2 plus 1.2x. Okay, the curve here. So this is the least square regression lines. This one is the least square regression line. Okay, yeah. So this is the best fit curve, okay, of the data, okay. And this one for your reference, or we have another lectures to focus on this one. Okay, we don't have more time, so just skip this one. And we have one more lectures to discuss about space, space, vector space. Okay, and maybe next time I will back to these slides and mention to you. But actually, we have one more lecture to discuss to mention about the spaces. Okay, so we finished the lecture today, and I hope you enjoy it. And if you have any questions, you can ask TA. And remember, you need to submit your homework on time. The homework, let me check. The homework deadline of lecture 1 part 4 will be next 2 weeks, right? 31 December. Okay. Any questions so far? And now for TA, please check attendance. Okay. Today, now for TA, we'll check attendance. Remember, if you cut more than 4 classes, okay, you will fail this course. Okay, immediately. So now TA, check attendance, and then question and answers, from 12 to tell 20. Okay, yeah, check attendance and then answer the questions from the student. Okay, and we stop at tell 20. Okay, you just randomly check attendance. Now we have 170 students, so we just randomly check 70 students. Okay, and if they absent, okay, just highlight if some students are absent. Okay, yeah, and then when we finish the course, usually you give me the list of attendance check. Okay, and then I count, and you help me to count if they cut 5 class, they fail this course. Okay. Okay, so for goodbye. Today, so for, can you get my point?